Hello everyone, so welcome to lecture 7 of Statistical Mechanics, and this is a particularly exciting one this evening. So let me share my screen. Only 7 slides, but all of them are very important, and I'm going to do quite a lot of algebra. So in the last lecture, we did a sketch through derivation of the density of energy states, G of E. And remember that I said to you not to worry too much about that derivation. I wanted you to see it so that you've actually seen it derived for completeness, but don't worry too much about that derivation at this stage, because it does take a little bit of time to get used to it. And also when you see it in different contexts, that will also make it a lot more tangible, because it is very abstract. So here's our derivation of the density of states. But what you do need to know is that to calculate the partition function for our ideal gas, we take our density of states and we stick it in here, and we integrate from 0 to infinity of our density of states multiplied by the Boltzmann factor. And that gives us our partition function for a single ideal gas particle. So I've denoted that result here by Z1. So here's the algebra that we need to do. And remember, we could just evaluate this integral by looking it up. We didn't work it out ourselves, we looked it up. And this is our result for our single particle partition function. So when I said that you don't need to worry too much about the derivation of the density of states, you do, however, really need to be able to take your partition function here and calculate thermodynamic quantities for it. So while the last lecture was something that you could, watch along to and not worry too much about it if you didn't think it made very much sense and you didn't really, it didn't really gel with you, no worries, just leave it. But for this lecture, these are things that we're going to be using all of the time. And actually, you sort of see me do this already for the paramagnet. So now we're going to do it for an ideal gas, and we're going to do a similar thing again later on for a quantum oscillator. And we'll also use partition functions a little bit for electrons and bosons. So this is going to crop up. And it crops up a few times. So it is important for you to be able to appreciate what is going on here and how I get from the partition function to the thermodynamic quantities that we can so helpfully extract from it. Okay, so this lecture is all about the thermodynamics of the classical gas from the partition function. Okay, so we're going to start from our partition function for a single particle, and then we're going to use Stirling's formula to get our n particle partition function. Okay, so our single particle partition function, let's write that down first. Okay, so that's our single particle partition function. And for n particles, Zn equals 1 over n factorial, Z1 to the power n. Now notice here that we have this n factorial in front of our partition function raised to the power n, and that is because our ideal gas particles are indistinguishable from each other. So we need to divide through by this n factorial to stop to prevent us from doubly counting states. Okay, so the first thing we need to do is to get rid of this factorial, and we're going to do that using Stirling's formula, and we're going to use Stirling's formula in a different form to how you've seen it before. So Stirling's formula can be written So it can be written n factorial equals n over e to the n. Now, this isn't the form that you're used to seeing it in. So for completeness, I'm just going to demonstrate to you that this reduces to the familiar equation that for Stirling's formula. Okay, so let's take logs of both sides. Okay, so we can take the n outside the log. Okay, and then we can split up this term here because of the logs. So we've got an n ln n minus ln e. Okay, and of course minus ln e is just 1. So we've got n ln n minus 1, which is n ln n minus n. So this is the formula that you're used to seeing Stirling's formula written in. So that's ln n factorial. So this is how you're used to seeing it written. But this form up here is completely equivalent. And that form is actually slightly more useful to us now, because now we can write down our n particle partition function. So we have Zn. So we start off with our 1 over n factorial, and we're going to take it from here. So we're going to get an e over n to the n. And then it's just our single particle partition function raised to the n as well. So then we've got times v times 2 pi mkt over h squared, all to the 3 over 2, and we're going to raise all of that to the power n for this n here. So this is our expression for our n factorial. This is our expression for Zn raised to the power of n. So of course we can stick all this inside the same bracket. That's going to make it a little tidier. So we end up with e over n v 2 pi mkt over h squared to 3 over 2 all to the n. And this is our n particle partition function for our ideal gas. So now we've got the partition function, we know everything there is to know about the physics of the system. So from this expression, we're going to be able to derive the internal energy, the free energy, and the equation of state. And it's just going to come out of here by magic, as if by magic. Okay, so we're in the canonical ensemble. So we suspect that the Helmholtz free energy is going to be a very useful quantity. So the Helmholtz free energy F is, so F is equal to minus KT ln, and I'm going to put in our Zn here for our n particle partition function, because of course we want to calculate the free energy of the whole gas, not just one particle. Okay, so we're going to get minus KT. We can take the n out to the front, so that's going to be n ln EV over n 2 pi mkt over h squared all to the 3 over 2. And now all of this is inside our log. Okay, so now from our thermodynamics, from our statistical mechanics, we're going to just swap back to our thermodynamics for a moment. So what we're going to do is we're going to write down the thermodynamic definition of the free energy, E minus Ts, which is entirely equivalent to U minus Ts, so don't let that confuse you. And we're going to calculate its differential form. dF is dE minus T ds minus S dt. And all of this should be very familiar to you by now, so don't be confused by the U and E switch, because I'm in statistical mechanics. So what we're going to do is we're going to use the first law to substitute for this dE, so that's T ds minus P dV, because we're dealing with gases, so our work term is going to be minus P dV minus T ds minus S dt. We can cancel these out, and as before, we've done this many times, dF is minus PdV minus SdT. So that's the differential form of our Helmholtz free energy. Now let's set T equals constant, and we can write partial dF at constant T is equal to minus P dV at constant T. And of course this minus SdT term is no longer there because dt is 0. So we get P is equal to minus dF by dV at constant T. So hopefully this type of derivation is now starting to feel very familiar to you. So now we've got this expression for the pressure in terms of the derivative of the free energy. So I can actually use this expression to calculate an equation of state from this. Okay, so we can do that now. Okay, so P is minus d by dV, constant T, of, so what we got in here, we've got a minus KTN ln, all of this stuff in here, EV over N. Okay, so we've got P is minus d by dV of all of this stuff in here. So the way that I deal with these is I've got a little trick. So we've got logs, and of course we can split up these logs however we like. And so we can split up these logs in such a way that makes our differentiation really, really easy. And I use this trick quite a lot. So we can write this as minus, oh no, minus, so those go away, that's convenient. So NKT, so we want the log of V, because that's what we're going to be differentiating with respect to. Let me just let's just get rid of that. So let's start because I've made a mess. Okay. Right, so we're going to do P is equal to, we've cancelled the minus signs, we've done that, NKT d by dv at constant t. That's the bit we forgot, quite an important bit. Okay, here we go. So now we're going to write this as lnv, because that's what we're differentiating with respect to. Plus right, so everything else in here, ln e over n 2 pi mkt h squared all to the 3 over 2. Okay, so what I did was I took this log and I split it up so that it's the sum of the log of v and the sum of log of everything else that I'm not differentiating with respect to. And of course, this is really helpful because we end up with nkt d by dv at constant t of log v, just 1 over v, and then d by dv of all of this is of course 0 because there's no dependence here on v. So we end up with P is NKT over V, which of course means that PV equals NKT. Exactly what we would expect. So we've managed to derive the ideal gas equation of state directly from the partition function. And some of you might be wondering, well, you know, Sarah, this was really quite long-winded, wasn't it? And actually, I knew the ideal gas equation anyway. So what is the point in going to all of that effort with the density of states and the partition function and to derive something that actually I learned when I was at school? Well, the point is that this machinery of statistical mechanics is entirely general. So when we wrote down our partition function, we considered particles that weren't interacting. But if we knew what the interactions between our particles were and we were able to include them in the partition function in the correct way, then we would be able to derive an equation of state for any set of interacting particles, and even if they weren't ideal. And so this enables us, even for systems where we don't know the answer, to obtain an equation of state. And of course, that's extremely powerful. So, okay, the next thing. So first piece of magic is done. Let's do the second piece of magic from the partition function. So actually, let's just go back to our slides. So we've gone from our partition function and we've taken our Helmholtz free energy and we've derived its differential form. We showed that this was true, and then we obtain the equation of state from the partition function. And of course, so here was our partition function. We defined the Helmholtz free energy. We differentiated minus the Helmholtz free energy with respect to V, and we got the ideal gas equation of state. So the next thing we want to do is get the internal energy. So we're going to use this expression E equals minus D log Z by d beta and our partition function to calculate the internal energy. So the internal energy Z equals minus d by d beta of ln. I'm going to put in our Zn for our n particle partition function because we want the internal energy of n particles, not just one. And just to remind you, because I never think about it anymore, it's just ingrained, beta is 1 over kt. Okay, so all we need to do is stick our partition function in and evaluate this thing, and it's going to drop out. It is really amazing. Okay, so here we go. So minus d by d beta of ln. Here's our n particle partition function. 2 pi mkt over h cubed to 3 over 2 to the n. Okay, so the first thing we can do is take the n out of the front. That's going to tidy things up a little bit, and also it's quite easy to lose these if you don't put them somewhere where you can keep an eye on them. D by d beta of ln EV of n Okay, now we want to do the same trick as we did last time of splitting up our log. So it's the sum of the thing we want to differentiate with respect to and the sum of everything else that we don't care about. So this is going to be minus n d by d beta of. Okay, so we've got a log of EV over n. And then everything in here we're not going to differentiate with respect to. So we've got a 2 pi and m over h squared. And that's 3 over 2. And then plus ln. And beta is 1 over kt. So if we've got a kt in here, that is a beta to the minus, because it's upside down, because it's 1 over 3 over 2. Okay. So now we get minus n. So of course, all of this is 0 because there's nothing in here that we're differentiating with respect to. So that just disappears. So we've got d by d beta of ln of beta to the minus 3 over 2. So let's take our 3 over 2 outside and put it together with our n. Okay. 3n over 2 d by d beta of ln beta, which is of course 3n over 2 times 1 over beta, which is of course 3n over 2 times kt. Exactly what we'd expect from the classical equipartition theorem. So what we've done is we've taken the machinery of statistical mechanics and we've been able to demonstrate that in the case of the ideal gas, we get the expected result for the equation of state, and we get the expected result for the internal energy that agrees with the classical equipartition theorem. So that's really, really fantastic. So we've managed to derive that the energy of our system is 3/2 nkt, exactly as we'd expect from the classical equipartition theorem. Now we can also get the entropy of the ideal gas if we like. So we've got our free energy here and we've got our energy here. So we've derived both of these things already. And of course, the free energy is the energy minus T times S. So it's a simple algebraic rearrangement to get the entropy of the classical gas. So that is the wonderful and fantastic power of the partition function. Once you've got the partition function, there is, you know, everything there is to know about the physics of the system. So enjoy and see you guys on Wednesday.